We are going to get back to C starting next week, taking a bit of a detour to talk about some more things related to Linux. Before we do, we need to understand a few of the fundamentals of operating systems. So that is what we are looking at in this topic. So we're going to briefly look at the history of Unix and Linux and see how we got to where we are today. We're going to look at some concepts generally related to operating systems. The Unix philosophy, so how Unix sort of views things and how its tools are built. We'll look at the main components of a Unix system, and then we will wrap up by talking about Linux briefly. To understand operating systems and sort of their value, we sort of have to start at the beginning before operating systems existed. So if we go back to 1945, they had just finished ENIAC, which was the first electronic general purpose programmable computer. But it has no operating system. And so in order to program it, these ladies were literally using thousands of switches and these plug boards where they would be plugging cables into like a switchboard in order to connect inputs and program the system. It was extremely time consuming, extremely cumbersome and error prone. It took them days and days just to input a very simple program into it. And they had to know pretty much everything about the hardware because there was no operating system to assist them. So, about a decade later, the first operating system rolls around as a joint project between General Motors and the National Aeronautic Association or something like that. They develop the first operating system for the IBM 704, a computer at the time. But it's not an operating system in the sense that we think of them today. At the time, computers just ran one program. And so their operating system was designed such that, okay, it runs one program, and then its job is just to move on and run the next program. So it was a batch processing system. Run one program, that finishes, automatically start the next program. 1961, we get the first time-sharing operating system. So before this, computers can only run one program at a time. MIT develops the CTSS, compatible time-sharing system, and all of a sudden now we have time-sharing. So we can say, okay, we're going to divide time into slices, and we're going to run, say, 3 programs. Each of them will get a turn. They'll get a slice of time. So program A gets to run. Now it runs for a second or two. Now program B runs. It runs for a second or two, and so on. So that's time-sharing, and that was invented at MIT. A few years later at Bell Labs, Ken Thompson and Dennis Ritchie, some of the developers of Unix, they develop Multics, which is sort of an ancestor of Unix. And so this introduces some advancements that later influence Unix. For example, the hierarchical file system, where we have this hierarchy in the file system starting with a root directory. That directory has subdirectories and so on. Okay, by 1973, they've released Unix at Bell Labs. It's the first portable operating system, so they had ported to C, as we've talked about, and that meant that as long as you had a C compiler on any system, you could port Unix to it without having to rewrite it all in assembly language. And of course, this is a very influential operating system. So not only is it portable, it's a time-sharing operating system, so we can run multiple programs on it at once, multi-user, we can have multiple users working with the system. And so it spawns quite a few both academic and corporate variants of Unix like BSD, Solaris, and so on, and we'll see those in a minute. 5 years later at the University of California, Berkeley, they released the Berkeley software distribution. This is a variant of the original Unix that goes on to be very influential. It contributes some significant advancements to Unix, one of which is the internet protocols. So you may have heard of protocols like TCP and IP. These are important protocols that are used to communicate over the internet, and they were added to Unix by BSD. Okay, the 80s were a time of the Unix wars, where you had AT&T now sort of branching off, and they released their variant of Unix called System 5, which was very commercially successful. It adds all kinds of advancements to Unix, so init scripts to start and stop processes, IPC, so inter-process communication, a way for processes on a system to talk to each other. And it becomes very influential for later operating systems like Solaris and AIX and, of course, Linux. Now, that same year, a hippie by the name of Richard Stallman. He's very convinced that, okay, we need freedom in everything we do with software. So we need the freedom to be able to do what we want with it, to modify it however we want, and we should be able to do anything we want with the software that we're using on our own computers. So he forms the GNU project with the goal of building a completely free operating system. Free as in freedom, not necessarily price. So free as in you're free to do what you want with it. You should be able to inspect its source code, modify it, freedom to do what you want. So they build over the years a ton of software, as we'll talk about in this topic. But one of their key contributions is the GNU General Public License, the GPL. This is a very important software license in the open source community. And basically it says, okay, any software that you license under the GPL, anybody can do anything they want with it. They can use it however they like. They can modify it however they like. They can distribute it. So they can change your software and now they can start distributing it. They could even charge money. So I could take your GPL licensed software, make some changes to it, and sell it myself. That's completely fine under the GPL. However, I have to provide the source code and I have to license any code that I write. So any changes I make to a GPL program, they also have to be licensed under GPL, and so anyone else has to be able to get my source code and use it however they want and so on. So it's a very important, they call it a copyleft license instead of copyright. And of course Linux is GPL licensed, so it's free and open source. So that was a key contribution from the GNU project. Now, late 80s, at this point, we've got a lot of vendors in the Unix game. Everyone and their brother has their own variant of Unix, and the problem for software vendors is that they don't all work the same. So if I write a program for, say, AIX, and then I try and run that program on, I don't know, Solaris, it doesn't necessarily run because they all have different system calls, different functions that are available on the computer, opening files, writing files, reading, and so on. All of their system calls are just a little bit different. So the IEEE, the Institute of Electrical and Electronics Engineers, they pick up on this and they say, all right, we got to standardize things here so that we have a common set, for example, of system calls, so that no matter what variant of Unix you're using, you can expect to have the same system calls like open and read and write and functions that are just sort of basic functions that a program needs. And so they create the POSIX standard, the Portable Operating System Interface standard, and that sort of provides a standard by which Unix vendors can now adhere to that POSIX standard. They provide this common set of functions, and now for the independent software vendors, they just have to write their software that complies to the POSIX standard, and they can be assured that it's going to run on any POSIX compliant Unix variant. Now 1991 rolls around, and a Finnish undergraduate of computer science, he sends out an email to, at the time this was called Usenet, so it was news groups, kind of like an ancestor to Reddit. So he sends out a post. He says, hello everybody out there using Minix. Minix was a Unix clone at the time. So he says, I'm doing a free operating system, just a hobby, won't be big and professional like GNU. Remember, the GNU project was trying to create their own operating system. So he's trying to create this free operating system for 386 and 486 AT clones. So he's referencing the Intel 386 processor, a popular processor at the time. He says, this has been brewing since April, it's starting to get ready. I'd like any feedback on things people like or dislike in Minix, as my operating system resembles it somewhat. I've currently ported Bash, so the shell. I've ported GCC, the compiler. Things seem to work. That implies I'll get something practical in a few months. I want to know what features people want. And he says, okay, yeah, it's free of any Minix code. So he wrote it himself. He didn't use anyone else's code. Has a multi-threaded file system. It's not portable. It uses a feature of the CPU he was using at the time. So it was not portable because he had coded it using a feature of his CPU. And it'll probably never support anything other than the kind of hard drive that he had in his computer, as that's all I have. So I include that just because it's kind of a cute little post in retrospect when we see how Linux has taken over the world And here's this like undergraduate student, just like you folks, over the summer. So what did he say here? This has been brewing since April, now it's August. So just over the summer, just writes an operating system, and then it of course goes on and takes over the world. So 91, Linus Torvalds releases the Linux kernel as a Unix clone. So it didn't use any of the original Unix source. It was just developed as a clone. And of course, then he soon afterwards adopts the GNU general public license. So it becomes open source. 2001 rolls around, Apple, so they had ousted Steve Jobs. They had fired him at one point. He went on to form a company called Next, which had an operating system NextStep based on BSD Unix. Steve Jobs gets rehired at Apple, and they base their newest version of their operating system, OS X, on NextStep, which is in turn based on BSD Unix. So they released that in 2001. About 6 years later, they released the first iPhone, which of course is based on OS X code, so also a Unix-based operating system. Following year, Android gets released by Google. They've taken the Linux kernel, they have optimized it for touchscreens, and it of course goes on and takes over the world and becomes the most popular operating system by number of installations. And then 2012, Red Hat surpasses 1 billion in revenue. So Red Hat is a big Linux company. They sell a variant of Linux called Red Hat Enterprise Linux, or RHEL. And that was the first year that an open source company had reached the 1 billion mark. So kind of a milestone, and again, kind of funny in retrospect to look at Linus's original post and saying, oh, it's not going to be big and professional, and now it's spawned like multi-billion-dollar industries, and that's not even counting the billions and billions of dollars of commerce that gets powered by Linux. This is a look at sort of the genealogy of Linux and Unix. You kind of have these three streams. So you have the original Unix at Bell Labs, and then we had sort of, at least to start with, the academic stream. So at University of California, Berkeley, they start working on BSD, and that goes on to be included in Mac OS, and PlayStation, you may not know, is also based on FreeBSD, which is based on BSD. So we had sort of this, like, at least to start, an academic stream. And then we had the commercial stream with System 5 at AT&T, and there were quite a few vendors in the Unix game at that point. Silicon Graphics, they were big in computer graphics at the time. They had their own. IBM had AIX, or has AIX. Sun had Solaris, Hewlett-Packard, HPUX. And then you had your clones, which didn't use the original Unix code, but sort of wanted to emulate Unix. That brings us to what is an operating system. So an operating system is in charge of managing the computer's hardware and providing sort of a convenient environment for users, but also a safe environment in the sense that it keeps you isolated from one another. So it's charged with allocating the resources of the computer. So if a program asks for memory, the operating system has to figure out a way to get it some memory. Scheduling the execution of programs, so when each program is allowed to run on the CPU. Of course, isolating users and programs from each other so that they can't crash each other's programs. Providing a user interface, and then of course providing an interface to programs so that a program can be assured that it has a standard set of functions that it can call, like functions to open files, to read files, and so on. And then of course just abstracting away the specifics of the hardware so that our software doesn't have to care about what hardware is running on the system. It can just focus on solving its problem. So before we had operating systems, again, we're going back now to, say, ENIAC in 1945. We don't have an operating system there. The computer is just a machine that is built to execute machine language instructions. And so if you don't have an operating system, you've just got the computer hardware, how do you get it to do anything? And the answer is that you have to write a program that just does everything. It solves your problem, but it also has to then worry about all aspects of the hardware, how to get input from the user. You can't just call a function scanf. We have to figure out how to allow the user to type keys and how to read from that keyboard and so on. And of course, back in those days, they didn't have keyboards. So you had to manage all aspects of the hardware, including solving your problem. And your program was all the computer did, right? They could only run one program at a time. So without an operating system, Each program is running directly on the hardware. It, again, has to do everything. It's got to solve the problem, but it's also got to manage everything. And so because of that, each program also has to know all of the details of all of the hardware it's using, right? Your program it's not going to be portable. It's going to be written for a specific device, and it's going to have to know how to manage that device in its entirety. And then, of course, if the hardware changes, then the program's going to have to change as well. Hardware is going to support only one program at a time, of course, because we don't have an operating system to switch between programs. And so each user is going to have to wait until the previous program is done. So what this all boils down to is that writing programs becomes extremely complicated and extremely expensive. So I include these pictures here just to sort of give you an idea. Now, this was 1970. At this point, these guys probably have an operating system. But this is how programming was done back in the day. Right? Those guys are not sitting at computers, they're sitting at these key punches. And all these key punches do, they press their little keys and they punch holes into these paper cards, into punch cards. And so that was how they would program, right? They would write their little instructions in machine code or in assembly language by punching out these holes. You would take your big stack of punch cards to the computer room, because we didn't have computer labs at that time. There was just one computer in a given department. And they would give their big stack of punch cards to the computer operator. This was an actual job at the time. Somebody would be sitting in the room, they're the computer operator. So you hand your big stack of cards to the computer operator, and when it's time, the computer is now free, it's done running whatever program it's running. Computer operator takes your stack of cards, puts them in the little feeder, they get read into the system, and now your program is running, and it's the only program running on that computer. So very, very tedious. I mean, can you even imagine? You know, we have all these tools today to point out, okay, you've got an error on line 6 or whatever. Here, can you even imagine trying to debug a big stack of these cards and try and find, you know, the one place where you mispunched a card? We're spoiled today. We're spoiled. So with an operating system, the operating system now runs on the hardware, and it hides the management of the hardware. It handles it for you. It abstracts away the details of the hardware so that your programs have a much simpler interface. Instead of having to worry about, you know, writing the code to go to disk and read a block off of the disk, I just call some function provided by the operating system like read, and it handles the details of that for me. If the hardware changes, of course, my software doesn't have to, because the operating system is abstracting away the details. And then by managing the resources of the computer, we can now run multiple programs. We're going to talk about time sharing in a few minutes. So it allows us now to run more than one program at the same time. And so what that boils down to is, of course, software then becomes much, much easier and much cheaper to develop when we don't have to worry about the details of managing hardware. So benefits of an operating system: manages the computer. It makes programming the computer easier. We don't have to worry about hardware. It even makes using a computer easier. You don't have to be an expert in the computer anymore in order to use it. Your grandma doesn't know the details of, you know, Intel x86 assembly language just to browse Amazon.ca. She just uses the operating system interface, and the operating system handles the details of the hardware. It abstracts the hardware, so our programs become portable. I can write a program for Linux, for example, and I know that I can take that to any Linux system and it's going to work because they have the same interface. So programs become hardware independent. And of course, it facilitates resource sharing. So I can run several programs at the same time. Several users can be sharing the same computer at the same time. So resource sharing. How memory and disk space are shared by an operating system. So it is enforcing isolation. So you've got, in this example here, we've got 3 programs loaded into memory. It is the operating system's job to keep them all separate from each other, so that, you know, program A cannot overwrite blocks of RAM, blocks of memory of program B or program C. The operating system keeps them separate. And if program A tries to read, say, some memory from program C, then the operating system has to intervene and say, nope, you're not allowed to do that. So yeah, we use isolation and we use permissions as well. So for disk, of course, we use permissions to keep programs from accessing each other's data on disk. Now, when you're making I/O requests, so let's say we're trying to read or write to a bunch of files, your program may have to line up and wait. So its requests may be queued in a buffer, and the operating system will then sort of process the queue and, okay, we want to read this file for this program. Okay, we want to write that file for that program. So your program may have to wait in order to get access to the disk. And so while it's waiting for its request to be fulfilled, whether it's reading a file, writing a file, whatever, it may be in a state where it is blocked. And we'll talk in a minute about why that's important. But just know for now that, okay, so if my program issues a command or calls a function to read a file, it may have to wait before it can get that data back from disk, either because some other program is using the disk, or because disk is just really slow. When we talk in terms of computers and we look at a CPU compared to the disk is just dinosaur slow. All right, so it may have to wait for a little bit in order for that data to come back, and while it's waiting, it's in a state where it is blocked. Other I/O devices on the network, or on the system, I should say, so network interfaces, printers, USB devices, again, the same sort of thing. The operating system has to handle any sort of resource contention. So if we have multiple programs, say trying to write data into the network, trying to send a packet of information over the network, the operating system can only send out one packet at a time. And so if you've got programs A and B there both trying to send, well then those are going to have to be buffered and queued up, and then the operating system sends them out one at a time. So once again, if I'm waiting for my packet to be sent into the network, I may be in a state where I am blocked. Another example is if I do scanf and I'm waiting for user input, users type really, really slow compared to the speed of a processor. And so while you're waiting for user input, the program is blocked. Brings us to time sharing. We want to run multiple programs at the same time, and so we use a technique called time sharing, where we break up time into slices. And we say, okay, this program's allowed to run for a little bit, now we're going to switch to this program, now we're going to switch to that program. And so the operating system is in charge of scheduling. We call it scheduling, the act of taking a program and starting to execute it on the processor, and then we schedule another process. We switch to another process, and now it runs for a little bit, then we schedule another, and so on. So when one program uses up too much CPU time, so maybe program A has been running for a little while, now the operating system decides, okay, you've had enough of a turn, we got to switch to somebody else for now. So it switches to another one. So if it uses up too much time, the operating system might switch. And then, of course, if a program gets blocked. So again, if we're waiting for our packet to go into the network, we're waiting for a response back from the disk for a read operation, our program is blocked, the CPU is going to say, okay, you're waiting on that, I'm going to switch to somebody else while you're waiting. Okay, that is called process scheduling or task scheduling. So the net effect is that each of the programs on the computer believe that they've got the computer to themselves. And you might look at this and think, okay, we got process 2 there and process 3. Oh, process 3 is sitting there blocked for a long time. It's not running. In reality, this is fractions of a second, right? It's super, super fast. So even though process 3 is not running for a while there, it still feels like it's really fast, and it doesn't know that it's been put on hold. It just happens so fast. So just an example to drive home the point. We've got 5 programs here on the computer. Process A starts running, and maybe it tries to send a packet into the network. So it has to wait for that packet to be sent out. And so while it's blocked, the operating system then moves on to program B. Program B starts running for a little bit, and then it issues a call to read a file from disk. Of course, disk is super, super slow compared to the processor. So it's blocked, waiting for that response to come back from the disk. And so the processor moves on to process C, to program C. And program C starts running, and okay, it does a scanf, now it's waiting for user input, so now we're blocked, and so we switch to process D. Process D runs for a while, then the CPU decides, okay, you've been running for quite a bit of time now, we got to give somebody else a turn. So it switches to process E. And process E is, there's just a little thought bubble there saying, is this system really shared? Because even though process E hasn't been running that whole time, again, this is happening in fractions of a second, so it feels very, very fast. And you can see this phenomenon if you SSH into compute.gall. If you SSH into compute.gall and you're sitting there typing at the shell, you're not noticing that the CPU keeps switching to all kinds of other processes. It just feels responsive. It feels like you're the only one on the system. And that's because this is happening so fast. I've been using the term process, but we haven't yet defined it. So a process is operating system terminology for an instance of a program that's running. So you've got your program on disk, you run it, it becomes a process. And the operating system maintains a special data structure called a process control block, a PCB, that contains information about every process that's running. So you're going to have, for example, a unique identifier, the PID or process ID. You're going to have its current state. So is it currently running? Is it executing on the CPU? Is it currently blocked? So it's been suspended and it's waiting maybe for a disk read to come back. Is it ready? So in other words, it was suspended, but now it's ready to be executed again. So maybe the disk read completed, or maybe we just switched away from it because it had used too much time and it's ready to be run again. Okay, so the current state of the process. We can have different priority levels, so we could have higher priority processes that maybe get scheduled by the CPU more frequently. And then we have a bunch of data that is related to suspending and resuming processes. So the program counter, that's the address of the next instruction to run. When we suspend a process, we need to remember, okay, where were we in the program, so that we can wake it back up and pick up where we left off. So it'll store the current program counter, it'll store all of the memory pointers, so all of the memory it has allocated, and then context data like the values of the CPU registers. So those of you who have taken CS2208, you'll know about CPU registers, right? Storage locations on the CPU itself that a program can use. When the program gets suspended, we have to save all of that data so that when we resume it again, we can restore all of that information. So all of that is stored in the process control block. There is a command we can use to view our processes on a system, and that is the top command. So top will give you a real-time view of what's going on your system in terms of all of the processes. You can see we've got their process IDs, what user is running them. There's some columns related to RAM, to memory usage. We've got their current CPU utilization in percentage, their memory utilization, how much CPU time that they've used in total, and then the actual command. Okay, so this gives you a real-time view of the processes over your system. If you use your less than and greater than keys, you can change the column that's being sorted. So I can move over and I can sort by, where am I here? There we go. So now I'm on the CPU column. I can go to memory, sort by that, see what's using the most memory, and so on. Okay, so that's the top command. That's a command that if someone were to call up and say, hey, the server's really slow today, one of the first things we would do is SSH into the server, load up top, and just see what's going on. For example, last night when I was looking through these lecture notes, I SSH in, and there's a student running some Java program using 100% of the CPU, and that's not uncommon. To get out of top, you press Q. And if you want to filter the output of top to a particular user only, you use -U. So if I wanted to see only my processes, I can say top-U, JSONs4, and then that's only my real-time view of my processes. So that's the top command, real-time view. We also have the PS command, process status, which gives us a snapshot of the current processes. If I do PS, by default, I'm only seeing my own processes. If I want a little bit more information, I can do PS-F, which gives me a full format listing. And so that just gives me a bit more information. So we have our process ID for each one. We have the parent process ID. So you can see, for example, I ran the PS command, and its parent process was this one here, bash, right? I was using bash to execute the PS command. We've got the start time, what terminal it's on, and yeah, how much CPU time it's used. So that's the PS command. It gives you a snapshot of the current processes. Again, if you want to filter them to a given user, I could type ps-u and then the username, and that gives me all of my users' processes. So you can see I've got a few more here. The reason being that PS by default only shows you your processes in your current tab, in your current session. So if you want to see all of them, you can use -u. And then finally, if you want to see everyone's processes, you're going to use ps-e, and I will generally combine that with F to get a full format listing. So ps-ef gives me all the processes running on the system, and yeah, so you can just get a snapshot of what's going on the system. We're going to see later in the course when we talk about process control that we can use this information, for example, to kill processes. If you have, say, a process stuck in memory, you could find it with top or with PS. I could see, oh, I'm using a lot of CPU usage, and then I could get its process ID and use the kill command to actually terminate it. Sort of like the end task in the Windows Task Manager. Okay, so talking about Unix philosophy, and this is kind of a stupid caption that I wrote. It's not that Unix is hard, really. It's just that it's different. It has a different philosophy. So Unix was never meant to be a user-friendly operating system. It's meant to be helpful to the user, right? It's meant to be powerful, to give you the tools that you need, and then just to stay out of your way. It's also, you have to keep in mind that Unix and Linux protect you from each other in the sense that they isolate you, but they don't protect you from yourself. So they will isolate our processes from each other so that I can't crash your processes, you can't read my memory, you can't access my files, that sort of thing. So it's meant to keep us safe from each other, but the operating system assumes that we know what we're doing. And a user can easily harm their environment. They can crash their own processes, delete all of their own files if they're not careful. So yeah, you can very much mess up your own environment. The operating system will let you do that because it's assuming that you know what you're doing. And so within the permissions that have been given to you on a system, it allows you to exercise full control. Now, the philosophy of the Unix tools is to keep every tool simple. So have it be razor focused. Have it do one thing and do that one thing really well. The other thing you'll find is that most of the tools are very terse. They're not very talkative. They don't have a lot of extraneous output. They just give you the base information that you need to know. And then the thinking there is that, okay, we've got all of these simple tools, but what we can do is allow the user to combine them together in order to accomplish more complex tasks. So we're going to see later in the course shell scripting, where I can write a script, and sure, I can use all of these individually simple tools, but then I sort of combine them together in a script to do something more complex. We're also going to see pipelines, where I can take the output of one command and pipe it into another command, which can then operate on that output, pipe it into still another command, which does further computations, and in so doing, in chaining those together, we accomplish a more complex task. So the reason for the philosophy that they've taken with these tools is, again, you have to remember when Unix was written, they were using like the PDP-7, which didn't have a monitor. It literally had a spool of paper that your output would print it out on paper. So you didn't want to have these tools spewing out screenfuls of text because that would waste a lot of paper. Okay. So we have been talking about the notion of a kernel, but we haven't really defined that. So if we look at sort of the three main components of an operating system, we've got the kernel, the shell, and then utilities. So the kernel is the core of the operating system. It manages all the processes, it controls the hardware, it does things like handling reading and writing files, writing to the network and reading from the network and so on. So handling all of the hardware resources and abstracting away all of the details of those resources so that programs running on top of the operating system or on top of the kernel do not have to care or know about how do I write a file to the disk or how do I read from a USB. They just ask the kernel for the data that they need in the form of system calls, so special functions that they can call that ask the kernel for certain information or ask the kernel to do things. Okay, so that's the kernel. We then have the shell. So we've talked about the shell already. The shell is the special program running on top of the kernel that allows us to execute programs and do things. When you SSH in, you are working with the shell, the bash shell in particular on compute.call. So it's called a command line interpreter because it is interpreting the commands that we give it. You will also hear people call it, working at the terminal or working at the CLI or the command prompt. Those are all just euphemisms for working at the shell. The terminal, if we're being technical, the terminal is the window that is used to access the shell. But you will often hear people say, I'm working at the terminal. They mean I'm working at the shell. Okay, and then we have utilities. So standard tools and applications that are bundled with the operating system. And they're sort of used so often that they just become part of the operating system. So things like ls, cp, mv, those didn't always just exist. At some point someone said, oh, wait a minute, we need a way to list the contents of our directory. So they created ls. And then other people said, oh, that's useful, and they bundle it with their operating system. And now it becomes a standard utility that's part of the operating system. Okay, so we'll wrap up this topic by just a few words on Linux. So again, if we're being technical, Linux is not an operating system. Colloquially, you will hear people say, I run Linux. I run Windows, oh, I run Linux. But Linux is not actually an operating system. It is a kernel. It's the part of the operating system that manages the resources, schedules, processes to run on the CPU, and so on. So the Linux kernel gets bundled together with all sorts of software to create a full operating system, but itself, it's not actually an operating system. Now, you will often see Linux noted online as GNU/Linux. The reason for that is that Linux is typically bundled with a ton of tools from the GNU project. So we talked earlier in this topic about how the GNU project, started by Richard Stallman, has been very influential in the Linux world. They've created a ton of software. So we've got things like all of the core utilities that you run on a Linux system, ls, cp, mv, all those standard utilities. Those were all written, at least for Linux, by the GNU project. The bash shell that we're using, written by GNU. Developer tools, the GNU C compiler, GCC. The GNU debugger, we're going to see that later in the course. Another build automation tool called Make, we're also going to see that. All of those written by GNU, and of course Emacs and Nano and tons of other products, all out of this project. So again, you will often see GNU/Linux online, and that just sort of reflects the fact that Linux is a kernel, GNU provided all of this software, and then together as a bundle, that's the operating system. Now, just one other note here. When we had looked at Linus's original email from 1991, he had talked about, oh, I'm developing this operating system. It's never going to be big and professional. I'm developing it for my 386, for an Intel CPU. Today, Linux is available for every architecture under the sun. So it's not just available for Intel. If you want to run it on a Raspberry Pi, so an ARM CPU, you could do that. And it's available for every other architecture. So not just Intel. I also feel it important to note that it's also not just what you see when you SSH into Gall. So that's working at the shell, right? You can install Linux on your computer. You can have a nice, beautiful graphical user interface, right? It's not just working in this boring little textual terminal. It does have a graphical user interface if you want it. Okay, so finally for this topic, you will hear the term Linux distributions or Linux distros. Those are, again, complete operating systems that bundle together a number of components. So we've got the Linux kernel, obviously, at the core. They provide system libraries, so the C standard library and other libraries that programs use to do things. You've got a set of software packages that come with each distro. And then you've got some sort of package manager, which is a piece of software that is used to install software, to update software, and to remove software from the system. So the package manager you can kind of think of as a cross between Windows Update and, if you know the feature in the Windows control panel, add or remove programs, you can kind of think of it as a cross between those two. So each distro adds its own customizations. It might add different theming and branding. If you install Ubuntu, it looks a lot different than if you install something like Fedora. Each distro will have their own set of software that they think everyone should have, that they will bundle with their distro. And then some may be more focused on, okay, we want to be really, really secure, and they focus on really hardening their distro, whereas others are more focused on, okay, we want to be user-friendly and maybe not be so stringent about security. So they will very much vary in their size, their scope, and who they are intended for. For general use, you'll see distros like Ubuntu, Fedora, Debian. If you're involved in any sort of security work, so as a cybersecurity researcher, you'll be using Kali Linux, which includes a lot of tools for penetration testing, so trying to hack into other systems in order to discover their vulnerabilities. If you're someone who really wants full control over your system and to be able to customize it, Gentoo and Arch Linux are good options. And then we have our enterprise computing options like Red Hat Enterprise Linux, RHEL. Oracle has their own distro, CentOS, Rocky. These are all distros where we don't want the latest and greatest. We want to be boring. We want things to be stable and rock solid. So a lot of our servers here, we were previously running CentOS, now we're running Rocky. And the idea being that I don't want some new package to be installed, some cutting edge new package that ends up crashing my system due to some incompatibility. I want things to be very stable and solid and not necessarily on the cutting edge. Now, one other point here is that Linux is free in terms of Libre, free as in freedom, but not necessarily free gratis, right? Not necessarily free as in beer. So free as in freedom, we're saying, okay, the GNU public license, the GPL, it mandates that you have to have access to the source code. You have the right to do whatever you want with the software, to modify it however you want, and then to distribute those changes. But whatever you distribute also has to be licensed under the GPL. You have to provide your source code to other people, and they can do whatever they want with your software. However, it does not mean that it's necessarily free in terms of monetary value. You can, and many distros do, charge money for Linux. So all of those enterprise computing options, those generally cost money. You pay for updates, you pay for support. Okay, so there's nothing in the GPL that says you can't charge money for the software. It's about free as in freedom, having the freedom to do what you want with the software. Okay, so we looked at the history of Unix. We saw that there were three main branches from the original Unix. There was sort of, at least to start with, the researchy side at Berkeley with BSD. And then that went on to spawn things like OS X and the PlayStation operating system, FreeBSD, and so on. Then there was sort of the commercial stream with System 5, and then that went on to spawn things like Solaris and IRIX and AIX and all kinds of other commercial variants. And then we had the clones, which didn't use any of the original Unix source code, but they were trying to emulate Unix. We talked about the benefits of operating systems, what they do for us, and what life was like before we had an operating system. And then we talked about resource sharing, so how resources on the system are shared, how we do time sharing to run multiple programs at the same time. Looked at processes with the process control block. We saw the top command for a real-time snapshot, PS command for just a snapshot of the current processes. And then we looked, of course, at the Unix philosophy. Again, we're trying to be user-helpful, not user-friendly, and have focus tools that do one thing and do one thing well. We've got three components of a Unix system: the kernel, the shell, and the utilities. And then we saw, of course, that Linux is a kernel, not an operating system, so it's often referred to as GNU/Linux. Any questions about that before I move on? Yep. Sorry, what is that? So we run a number of distros. In the back end, we run Rocky, which is based on Red Hat Enterprise Linux. On Compute.all, we're running Fedora. We wanted something a little bit more cutting edge with like more up-to-date packages for users who were working. But yeah, on the back end, we usually run things that are a little slower. So they don't receive the latest and greatest package updates quite as quickly because, again, the focus is on keeping things really stable and secure so that we don't have to be called in on our holidays because some package got updated and all the servers crashed.